This video is the first of three videos describing a new addition to Statgraphics Centurion version 20 for dissolution analysis. Dissolution analysis is used to analyze the pattern of dissolution of a drug or substance over time. It's an important aspect of pharmaceutical development and quality control. There are two important elements of dissolution analysis. The first is characterization of the rate of dissolution for a specific product. The second is the comparison of two products or formulations, such as a brand name product and a generic. The discussion of dissolution analysis in Statgraphics version 20 is divided into three videos. Part 1, which you're watching now, deals with fitting dissolution models. Part 2 covers model-dependent comparisons, and Part 3 covers model-free comparisons. A typical data set for a dissolution analysis consists of measured dissolutions at 3 or more times after release begins. For comparative studies, the FDA recommends that at least 12 dosage units be studied for each product or formulation at each time point. In our example, we measured 12 units each of a reference batch and 5 test batches at 30, 60, 90, and 180 minutes after dissolution began. In Statgraphics version 20, the data may be formatted in either of two ways. First, the data for each unit tested may be placed in a separate column. Second, all dissolution measurements may be placed in the same column and code columns created identifying the batch, time, and unit. Here's a data sheet with the sample data we'll analyze, arranged using the first approach. There's a column for batch, a column for time, and 12 columns, each containing the measurements on a different unit. Here I have the sample data loaded into a Statgraphics data sheet. To perform a dissolution analysis, I'll go to the top menu to relate, and then to the far right where it says dissolution analysis. There are three options: dissolution model fitting, model dependent comparisons, and model free comparisons. In this video, we'll look at dissolution model fitting. The first dialog box displayed lets us specify how we've formatted our data, either as multiple data columns or as data and code columns. The second dialog box is used to specify the columns that contain the batch identifiers, the times, and the dissolution measurements. I'll then see a third dialog box with analysis options. I can specify up to 10 popular dissolution models to fit to the data from each batch. I can also tell it whether to estimate the maximum dissolution parameter in those models or to use a value that I will specify. Here is the output that was generated when fitting our sample data. You see the calculated R-squared and adjusted R-squared statistics for each of the 10 dissolution models. The best model for each batch is highlighted in red. You'll see that the Weibull model was best for 2 of the batches. The Hopfenberg model was best for 2 other batches, and the Gompertz model was best for the final two. A table is also generated showing the estimated parameters for each model and each batch. There are up to 3 parameters for these various models. All of the models have a rate parameter. Many of the models also have a second parameter, such as a shape parameter. And all of the models except the zero order model have a maximum dissolution parameter. Statgraphics will also plot the fitted models for a selected batch. Here you see the fitted models for the batch equal test 1. Notice that some of the models pick up the shape of the dissolution profile much better than others. You can also use analysis options to remove unwanted models to simplify the plot. Here you see the best fitting model for test 1, which was the Hopfenberg model. It does a very good job of picking up the patterns in the data. Since nonlinear least squares is being used to fit the dissolution models, it's a good idea to plot the residuals. The residuals are the difference between the observed measurements and those predicted from the fitted model. For a good fitting model, the residuals should vary around 0. Because of the popularity of the Higuchi model, a special plot is offered in which the dissolution measurements are plotted versus the square root of time. If the Higuchi model fits well, the points will be close to a straight line. Here you can see some lack of fit of the Higuchi model, which wasn't the best model for this particular batch. A similar plot created by the model fitting procedure is the Pessis plot. This plot plots the log dissolution versus the log of time. If the Korsmeyer-Pessis model fit the data well, the points would again be close to the line. In part 2 of these videos, we will test whether the dissolution profiles of the test batches are different than that of the reference batch. We will use the models that best fit each of the test batches.